Hello friends, it's Kalpesh Chani and I welcome you all to this video presentation. Friends, we know that our country is passing through the pandemic of COVID-19 and the whole world is right now passing through the pandemic of COVID-19 and you are at your home. So I thought you can spend this time continuing your study. So I have prepared this video presentation for you. The topic that I have selected is the topic of diffraction. Some of you have told me that this topic is a little difficult to conceptualize, so I have taken this topic. It is a part of BSc Physics Semester 2 syllabus of Saurashtra University, paper 201. So we shall deal with this topic in 3 or 4 video presentation. In this particular video presentation, I shall talk about I shall take the introduction part of this particular phenomenon of diffraction. So let us start this topic. So friends, this video presentation would cover this many points. We shall start with the definition of diffraction and its general understanding. Then we shall take the understanding of waves and its properties. Then we shall take the propagation of wave in terms of wave fronts. So we shall introduce the concept of wave fronts. And then we shall have the Huygens principle for the formation of wave fronts. And we shall also discuss the type of wave fronts. And then, and last, we shall interpret the diffraction from the point of view of wave fronts. So let us start with the topic of diffraction. So let us start this topic of diffraction. Some people also pronunciate it as diffraction. So we shall come to this term in a short while, but we shall start with looking at this photograph which is shown in this slide. In this photograph, one object is shown which is an arrow mark, and it is illuminated by a source of light, and its shadow is formed on the screen, as you can see here. Now if you look at the boundary of this shadow, you will find that the boundary is fuzzy. So we shall start with why it is so. Actually, we should expect a very sharp boundary. Why? Because light travels in a straight path. So whatever the light rays which would be able to make to the screen would illuminate that part of screen, and the light rays which would not be able to make to the screen, that part of screen would be dark, uh, forming shadow of the object. So the edge or the boundary of the shadow should be very sharp, but here we get very fuzzy boundary. So why it is shown? In our everyday experience also, you will find that the shadows of so many objects are fuzzy actually. So why it is so? You may say that there may be several reasons for this. The light rays which are falling on the object may be coming from different sources, may be coming from different directions, and so forming multiple shadows at the same time, and these all shadows overlap each other and making the boundary of the shadows blur. Okay, that may be one of the reasons. And secondly, you may also say that the object itself may not be having very sharp edges or the surfaces, then the shadows of them uh, would also be blur, having blur boundary. Okay, but we can eliminate here in this case these two reasons. We can have a single source of light. Suppose we take only a point source of light, and that too the source which is emitting only single wavelength of light, and we take the object to be having a very sharp edges. Now in this case you will get the shadow of the object having blur boundary, having very fuzzy boundary. Now what is the reason for that? So that we have to go into uh, what we can infer from this type of behavior, the fuzziness of the boundaries of the shadow. So let us start with what we expect. Actually we expect, as I have told, that we expect that the light must be traveling in the straight line. So we take some of the representative rays of lights which fall on the edge of the object, and then we shall project these rays on the screen. So we get these points on the screen. So we have taken some representative light rays originating from the point source, falling on the edges of the object, and they would trace some point on the screen. And if you connect these points on the screen, you will have an outline, and this outline is what we call the geometrical shadow. That is the shadow which we expect the light should be forming on the screen. Outside this outline there must be an illuminated region. Inside this outline there must be a dark region. So shadow must be within this. This must be the boundary of the shadow, very sharp boundary. But actually we find that our actual shadow is inside this. It is smaller than this, the region of outside, which is uh, actually covered by this outline, and this shadow is also having a fuzzy boundary. So now what we infer from this is that the light rays which pass near to the just near to the edge of the obstacle, they do not fall on the screen at the point that we expect, but they fall inside this geometrical shadow. So these rays must have been deflected at the edge, from the edge of the obstacle. So we expect some type of deflection of the light rays which are passing at the edge or in the vicinity of the edge of the obstacle. So this is the inference that we can make from this fact of the fuzzy shadow. So let us first see this thing diagrammatically and have some historical information regarding diffraction. Then we shall proceed with the term diffraction. What does it mean? In the next slide. So historically, if we see, this diffraction term actually was given by Italian physicist Francisco Maria Grimaldi in 1660. He gave this term to the effect that he saw in the shadows of the object, and it was given as the name of diffraction or diffraction. So now let us understand what we have just talked about. We have talked about that we are finding the deflection of the light rays from the edges of the obstacle. So actually we have, suppose if we have to show it diagrammatically, we have a bunch of light falling on the object. Now some of the rays would be obstructed by this object, but some of the rays which would not be obstructed by the object, this would fall on the screen and form the shadow of the object. But as we have told that these rays do not reach on the screen going straight, uh, having a straight path, but they are found to get deflected from the edge of the obstacle. So their path is not as shown in this diagram, but they are tracing the path uh, as shown in this modified diagram. Here some portion of waves are found to have been deflected from its direction of propagation, and they reach to the interior part, little interior region of the geometrical shadow. So they will infiltrate inside the geometrical shadow, making the real shadow smaller than the geometrical shadow and making the boundary of this shadow fuzzy. But if we look at the boundary of the shadow, if we have taken only a single wavelength and we have taken a point source, and if we look at the boundary of this shadow in a much greater detail, this fuzziness is not just the blurriness, but actually it has a formation of some type of fringes over there. So let us look at it in the photo that we have seen in the first slide. Let's go back to that slide and look at the boundary in a very detailed manner in the next slide. So let us again inspect a portion of the boundary of the shadow in this photograph in a much greater detail, and let us try to see what this fuzziness is all about. So we shall take a part of the boundary of the shadow as shown in this red rectangle, and we shall zoom this portion and try to see what this fuzziness is all about. So when we zoom it, we find that this fuzziness is actually this type of formation of some type of fringes here. You can see the formation of fringe in the shadow region, the boundary of the shadow, and these fringes just grossly look like a fuzziness in the boundary of the shadow. So this formation of these fringes actually is there, and so these fringes are known as the diffraction fringes, and this phenomenon is known as the phenomenon of diffraction. So if we have to grossly define the phenomenon of diffraction, uh, it is the bending of light rays from the edge of the obstacle and subsequent interaction of this bent light rays with each other, going into some type of interference, and this whole bunch of phenomena, the bending and subsequent interference, uh, is known as the phenomenon of diffraction. So actually diffraction is a bunch of these two phenomena together. So let us now go to the detailed understanding of this diffraction in the next slide. So by now we have had the general understanding of the diffraction phenomenon. At first it was observed for the case of light rays, so it was at first believed to be an optical phenomenon, but later on it was established that it is a wave phenomenon because it is applicable to all type of waves. Light waves are one type of electromagnetic waves, but it is applicable, this phenomenon is applicable to all type of waves, whether they are sound waves, whether they are other material waves like the waves passing in the medium of a stretched string, or the waves which are set on the surface of water, etc. So it is applicable, this phenomenon is applicable to all type of waves, whether they are matter wave even, it is applicable to all type of waves. Now we in this slide would understand the basic properties of wave, and for that purpose I have created this animation. As you can see in this slide, uh, there is a wave motion shown. Two waves are shown here which are moving in left direction. Now this may be the case of you can call it a transverse wave, something like the wave which are passing on the medium of a stretched string. So you can consider it as a stretched string, and you can see some points oscillating on the wave here, they are shown. Now these points are the representative points, or they are representative of the constituents of the stretched string. So in stretched string, you know that all the constituents are connected with each other by some type of elastic forces. So when you set the first constituent of the stretched string into an oscillatory motion in the perpendicular direction, the energy that you expend in doing so would be exchanged by the first constituent to the other constituent, next constituent, and that constituent would be set into an oscillatory motion, and subsequently all the constituents would be set into the oscillatory motion, and thus we can see that wave is formed and wave is propagated in the medium of a stretched string. So here these points resemble, or these points actually are the represent these constituents, the points which are oscillating in the y direction as the wave moves. So the first parameter of the wave is its wavelength. How can we define the wavelength? As you can see here, uh, just look at the first constituent. When it completes its one oscillation, the portion of wave that is moved in the left direction is known as its wavelength. So by the time the first or any constituent completes its one oscillation, some portion of wave moved has moved in the left direction. So wave has its own uh, velocity of motion. It propagates in some particular direction with some particular value of motion, so it is known as wave velocity. And the portion which actually passes of the wave during one complete oscillation of its constituent is known as its wavelength. It is denoted by the letter lambda. The second parameter is its amplitude of the wave, and you know what is the amplitude of the wave. When there was no wave effect, all the constituents were at its mean position, and when they come under the effect of wave, they start oscillating, and the maximum uh, distance that traverse on y-axis from its mean position is known as its amplitude. So this is also very clear. And the third point, the third parameter is known as the phase of the wave. Now to understand the phase of the wave, I have drawn one other circle which is having the same radius as that of the amplitude of the wave, and I have drawn one point which is moving on the circumference of this circle, but it is moving in such a synchronization with the constituent uh, of the wave, such that it resembles the y displacement of the constituent of the wave at any time. So if you look at any time the y displacement made by the constituent, the point also has made the same displacement on the y-axis, so they both resemble each other. So they are shown by the line connected between the both, so they both move in synchronization on the y-axis. So now let us understand the phase of the wave. So we can say the phase of the given constituent at a given point of time is the angle which this point moving on the circle subtends with its center. So suppose I stop this animation at one point, and if I just give the angle which this uh, point on moving on the circle has made, which resembles with the displacement made by the constituents on the y direction. So this actually angle is known as the phase of the given constituents of the wave at a given time. So this is what the phase of the given point of the wave is all about. Now each and every constituents on this wave uh, have always changing value of their phase. So we can say that as the wave passes, all the constituents changes its value of phase. So this phase resembles, it tells us at which portion of the wave we are looking at. Suppose you take the position, y position of any one constituent, then at which position of the wave we are looking at, that is actually uh, shown by the value of phase. Because you may be, if you take one total wavelength, there are two positions. Suppose you take one point here, it is having some value of y, but this point is also having the same value of y. So whether you are looking at this point of the wave or you are looking at this point of the wave, it is not clear from its y position alone, but it can be made clear by this angle which the uh, point on this point on this circle subtends with its origin. So this is known as the phase of the given point on the wave, and this is shown by this relation y is equal to a sine theta. We can represent this wave as a variation of sinusoidal function. So the value of y, you work out the value of phi from this value of y, from this. So this is how we come to know about the phase of the given point on the wave. So now in this slide you will see we have already learned what is the phase of any point on wave. So in this particular animation you will see that as the wave moves, we can take this as the motion of the phase point of the wave. So as you can see here, all the points which are at crest of the wave, suppose you take a crest of the here, then this point go on moving in this direction. So the motion of wave can be regarded as the motion of phase points in one particular direction, that is in the direction of wave propagation. So these points are the constituents of the medium, but here we are talking about the point which are the point of wave itself. We are not talking about the constituents, we are talking about the points of wave having some value of phi. So now if we take all those points which are having the same value of phi, that is the phase, and suppose you actually take all those points, not only of this one wave but all the other waves which are having the same value of phase phi, then it will make one set of points. Here this line here, the vertical line here which is shown are those set of points which represent the same phase, and as you can see, these lines move with the wave. So we can say that all set of points which are having the same phase move with the propagation of wave. Now this can be termed as wavefronts. So what are wavefronts? Wavefronts are the set of the phase points having the same value of phase. So there may be n number of waves we consider, and we take out the points which have the same value of phase, and the set of those points is just the wavefronts. Now if this set of all points construct surface which is of the nature of a plane surface, then they are called plane wavefronts. Some this set of points would construct surface which may be spherical in nature, then they are called spherical wavefronts. So let me show you in the next slide. Now we can regard this wave propagation as the propagation of these wave fronts. So now we shall just leave the idea of the conventional wave propagation, but now we shall go to the idea of the propagation of wave fronts rather. So let us first see this in 3 dimensions. I have prepared an animation in 3 dimensions which would just show that how these lines actually, if there are waves on the direction going inside this plane of the screen, then they would construct actually plane. So let us go to the next slide. So here you can see the same animation in 3 dimensions, that if you have all the waves and if you take the set of all the points which have the same phase value of phase, then this set of phase as this set of points will construct some surface, and if this surface is a plane surface, then they are called a plane wavefront. So here we can regard now the motion of these all waves in terms of this motion of plane wavefronts. So we can see now the wave as the motion of this plane wavefronts, and the distance between these two, any two this wavefront, is the distance equal to the wavelength of the wave. So let us go to the next slide. So here in this animation you can see, now we can regard all the motion of the all waves, propagation of all waves in terms of the propagation of wave fronts. So here they are the example of the plane wave fronts, motion of the plane wave fronts. You can regard these waves by the motion of plane wave fronts. So now let us go. Now one thing is that now we are disregarding waves by themselves and regarding the wave fronts. So as you know, as we have told in the first slide of the uh, wave general overview of waves, that one constituent which is set into the oscillatory motion will give rise to the oscillatory motion to the next constituent, and so on and so forth. So here when we disregard wave motion and we regard the wave uh, by just the propagation of wave fronts, then one wave front must be giving rise to the next wave front. So when we say there is a actually propagation of all these wave fronts, so the construction of wavefront, one wavefront must be giving rise to the next wavefront. And how then we can very easily understand that how one constituent of the wave sets the other constituent into the motion, oscillatory motion. But here how can we understand that one wavefront gives rise to another wavefront? Because we have disregarded the notion of wave altogether. So we have just to uh, take that one wavefront is giving rise to the other wavefront. So that we shall see. That is actually extraordinarily explained by the scientist Huygens, and we shall see its principle. We shall see its principle of the formation of wavefronts out of the one wavefront out of the other. Okay, but one question is still there: why we are looking at the waves in terms of wavefronts? Now, why we have disregarded waves by themselves and taken the concept of wavefronts? And it is because in the phenomenon of diffraction, if you have just seen that even if the waves which pass in the vicinity of the edge, they are getting deflected, so they do not interact directly with the boundary, even if they are actually affected by the edge of the obstacle. To understand this, we have taken this concept of wavefronts. That means that the portion of waves which are obstructed by the obstacle and the portion of waves which are not obstructed by the obstacle, these two portions actually are not totally independent. Actually, they are interrelated. The portion of the waves which is obstructed does not uh, leave the other portion of the wave to travel independently. When one portion of the wave is obstructed, the other portion of the wave is also gets modified, and that is the observed phenomenon is all about. So now we take the wave as connected to each other. So we are taking the wave in terms of wave fronts. So now when we now uh, give the phenomena in terms of the phenomenon of diffraction in terms of wave fronts, then we will see in the next slide what happens. As I have told you in the previous slide, that we cannot take the waves moving in the medium are totally independent of each other. We cannot take them as moving independently. So, suppose some bunch of wave is obstructed by the object, then the other bunch of wave which is not obstructed by the object is will go on independently further. This is not the case. Actually, in reality, we observe that they are modified, even if they have not directly interacted with the obstacle, but even then they are modified. So to understand that, so one thing is very clear, that these rays which travel in the medium, they cannot be taken independently, they cannot be taken as independent of each other. So the left side case is not the it does not represent the reality, but the case on the right side actually represents the reality. So to understand that, we have taken waves now in terms of wavefront, the motion of wavefronts. So here you can see that when you take the waves in terms of the motion of wavefronts, as the wave moves, wavefronts also moves. Here we have taken parallel waves, so there would be plane wavefronts representing parallel waves. Now when it is obstructed by the obstacle, then the portion of wavefront is actually cut off, and because of this portion of wavefront is cut off, the remaining part of the wavefront would be modified. As you can see here in this slide, that when the portion of wave here a portion of wave front is cut off, the remaining portion of the wave front is actually modified in this form. So wave cannot, this bunch of wave is not independent with this bunch of wave. That is what that is why we have taken the things in terms of wave fronts. Actually, the wave front is one whole entity which connect all type of waves together. So when an obstacle comes, the wave fronts get modified, and when wave fronts get modified, accordingly waves are also modified. So that is why we have taken the concept of wave front to understand diffraction phenomena. Now, but when we actually understand, when we actually uh, put everything in form of wave fronts, the one thing is still remaining, and that is, with the notion of waves we can explain why uh, the motion or the wave is set into the medium. One constituents affects the other constituents, constituents by constituents, uh, the energy is propagated and wave is set. But here when we take them in terms of wavefronts, how one wavefront gives rise to the other wavefront, that is not clear here. So it was the genius of Huygens that who gave an extraordinary explanation how one wavefront can give rise to the other wavefront, and he was also able to give reason for this type of modification of wavefront after it encounters an obstacle. Why wavefronts should be modified in this way? That was also explained by Huygens. So that we shall see in the next slide. Friends, we shall restrict ourselves to this point in this video presentation. The next things of the Huygens principle, Fresnel's theory, John Platt formation, and the other particulars which come under this topic of diffraction would be dealt with in the next video presentations. There would be somewhere around 4 video presentations on the same topic covering the full length of the topic. So keep watching. If you like this video, press like, and thank you for watching this video, and goodbye till then.